So this is problem set 3, exercise 4, and this is again the same problem, but this is the second part of the same problem. Okay, so now what we're going to do is we are going to calculate the same characteristic path length for a ring lattice. Remember that a ring lattice is something like this. Okay, so this is something like this. The number of edges attached to every node is constant. We have the same number on either side. Okay, so here we have on the left side and on the right side we have 2 links. So the degree is going to be 4 in this case. Okay, because we have 2 links on the left side and 2 links on the right side. So the total degree for each of these nodes is going to be 2m, which is, well, in this case is 4. So in general, when we have not only for this network, but I mean, this is impossible for a configuration model. Okay, the probability that this happens in a configuration model is impossible. But assuming that the formula of the configuration model makes sense in this lattice, I'm going to use that formula, and what I'm going to do is, since we have, I'm going to assume that that n is going to be very large, again, just like before, and this m is going to be constant. So let's see what happens. When I write the expression, okay, now the average degree is going to be 2m, okay? This is constant for everybody, and the average of k squared is going to be just like this, because it's constant, okay, which is 4m squared. So these two guys do not depend on n. So in the end, what I'm going to obtain is something which only depends on the logarithm of n. Okay, so here on the numerator I have the logarithm of, well, n minus 1 and so on and so on. Where are you? Here. So this is, okay, n minus 1, and then this other part which is only going to depend on m. I'm going to write it, but it's only going to depend on n, and then divided by this logarithm which is also only going to depend on m. So this is what we are going to obtain. And in the end, what we obtain is the logarithm of n minus 1 times 4m squared minus 4m. Okay, this is for the average. This part is for the average of k squared, and this part is for twice the average of k, divided by the average of k squared, which is 4m squared, and then a minus 1, and then divided by the logarithm of 4m squared minus the average of m divided by the average of m. So this is what I'm going to obtain. If I stick to the same rules as before, then I should get rid of this. I should neglect this part, and then neglect this part in the addition of logarithms, and then just, I mean, consider this, that this is just going to be included as a constant. So it's going to go like the logarithm of n when I make these things large. Or if I wanted to stick to something, well, I think it's okay to keep it like this, because this is a very unrealistic network. So I'm going to say that this is going to go like the logarithm of n, like in the first case. Okay, so this is the result. If not, I mean, if I wanted to be a little bit more precise, then L would go like the logarithm of n divided by the logarithm of the average value of k, because in the end, the logarithm of k squared, which is the logarithm of k squared in this case, is twice the logarithm of k. So it's going to be of the same order of, so I can write it like this, just to more or less to know the order of magnitude. And that's it.